Okay, so let's see. You're supposed to hit capture. Have you done that?
Yeah, I did.
Oh, very good. Okay. Okay, so at the end of last time, we were continuing our study of principal bundles by looking at examples, and we were talking about Grassmannians. And that's a very important subject, and I don't think I quite said it as clearly as I should have. So I'm going to begin today by saying a few things in a little bit more detail. So you remember that we have this F, which can be R, C, or H. And in the case of the quaternions, we have to take care about their non-commutativity. But then we can look at Fn, and then the Grassmannian of k-planes in n space for that F is equal to the moduli of k-dimensional subspaces of Fn. And this is a homogeneous space. Because, after all, GLN, by which I mean GLNF, acts transitively. Okay, it's clear that if you have two k-dimensional subspaces of an n-dimensional vector space, then there exists some linear, invertible linear transformation that takes one to the other. Now, to calculate the stabilizer, we could choose a standard k-dimensional subspace, which is spanned by E1 through Ek, where where I'm going to choose a standard basis of Fn. So let's choose E1 through Ek, Ek plus 1, up to En to be the obvious basis. So E1 is 1, and then zeros, and so on. So Ek has a 1 in the kth position and 0 elsewhere. And then if we choose if we choose that point spanned by, let's call it W0, which is the span of E1 through Ek, then what is the stabilizer? Well, the stabilizer will be matrices that look like this, where this is k by k, and this is n minus k by n minus k. Okay, so it's clear that as a homogeneous space, GLNF is equal, as a homogeneous space, the Grassmannian of k-planes in n space is GLN divided by GLK times GLN minus k. Okay. Now, we can get a little more insight into this if we introduce, let's call it VK non-compact of Fn, which is equal to the moduli space of k-dimensional spaces with basis. Okay, and then we can think of that as the set of k by n matrices. So it's W, or sorry, lambda in k by n matrices over F, such that lambda has rank k. That defines what's called the non-compact Steeple manifold. And so we could think of lambda as looking at something like this, v11 through v1n, dot, 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 vk1 through vkn. And so we can consider the rows of this matrix to be k vectors the k vectors that span our space. So W would then be the equivalence relation, the equivalence class of lambda under the equivalence relation that lambda is identified with h times lambda, where h is in GLK. Because left multiplication by GLK changes the basis on the space W. Okay, so this would be an element of the Grassmannian. Okay, it's in space. And then you can also note that that VK non-compact of Fn is also a homogeneous space. This time for the action of GLK times GLN. So we could act with lambda goes to H lambda G inverse, where H comma G sits in here. This is a left action, despite the fact that I'm multiplying on the right here. Because I put an inverse, this is actually a left action by GLK times GLN, and they commute. And again, we could choose a, so why is this a homogeneous space? Because this is a transitive action. And why is this a transitive action? Because the only invariant of a linear transformation under arbitrary changes of basis of the domain and the range, the only invariant of such a transformation is the rank. So put differently, any lambda can be mapped to the unit matrix here, and then 0. So this is k, this is k, and this is n minus k. Okay. And then what's the stabilizer of that? Well, you see the stabilizer will be a k by k matrix A here, and then a matrix that looks like this. Okay. So the stabilizer is GLK times GLN minus k. So therefore, BK non-compact is GLK times GLN divided by GLK times GLN minus k. And that is the same as GLN divided by GLN minus k. Okay. Now, it's also possible to use these lambdas to get coordinate systems. So, you see, now if we have a space, say a W, that comes from a lambda that looks like 1 through 1, and we fix the gauge, so to speak. We fix the, I should say one more thing. And the Grassmannians, the space of the Grassmannian is the quotient of GLK mod VK non-compact. That's the quotienting by the change of basis. So I can fix the gauge under this transformation by demanding that these this first k by k matrix be 1, and then I'll just have a bunch of numbers in general, A1, A1 through A1, 1 n minus k through AK1 through AK n minus k. And so then these are coordinates. Okay? So we can think of this matrix, this is a matrix of the form 1/A, where A is in matrices k by n minus k over f. Okay, so that's a local coordinate chart. And you see immediately that from that point of view, the dimension of this Grassmannian is equal to k times n minus k. Okay? But it's also clear what's the dimension over F? So the dimension over R is K times N minus K of G Grassmannian of K planes in N space for R, whereas the dimension over the reals of the Grassmannian of K planes in N space for C is 2K N minus K. And if I talked about the quaternions, quaternionic K-dimensional spaces, then I would get a factor of 4. Okay. Now, now these are not global coordinates, and maybe that's the first thing to understand. Why are these not global coordinates?
To move the columns around?
Yeah, right. So one way to say it is this. Let's let VC be the span of EK plus 1 through EN. Okay? So I claim that any subspace W, which has a set of basis vectors that looks like this, has the property that V intersect V complementary is the zero vector space. And why is that? Well, you see, any vector V which lives in this intersection here would have to be in the complementary subspace, but that means that its first K components would be 0. But if these are the basis vectors, you see, that would mean that the vector itself has to be identically 0. So matrices of this type span spaces W, which have this property. On the other hand, there exist W, which are subspaces of Fn, which have dimension K, with W intersect Vc as a dimension which is positive. Such spaces exist. So these cannot be global coordinates, but as you just suggested, it's clear what to do. Okay. So we can get coordinate patches by choosing subsets, I1, which without loss of generality, I can assume are ordered. Subsets of integers inside 1 through n. Let's call that S. And to such a tuple, I can do the following. Let lambda upper S be the K by K matrix obtained from these columns. In other words, to a tuple of type S, I take the columns, the K columns corresponding to these integers, I1 through IK, and then I can define my coordinate patch, U sub S, by the set of vector spaces spanned by lambda, where lambda upper S has non-zero determinant, which is the same as the set of vector spaces W, such that W intersect VS complement is the zero vector space, where VS complement is the span of the vectors EJ, where J lives in the complementary set of n minus k integers. Okay? So now, in the notes that I hand out, I say a little bit about how the transition functions work. So I think I'll leave those details to the notes. but I hope you get the idea that in each of these in each of these patches, you see in this patch, I can always choose a gauge, again by left multiplication. I can choose a gauge so that my lambda has the following form. I'll write it this way: 1 sub s and then a sub s. And the normal ordering signs mean that I should order the columns so that they are columns 1 through n. But I don't know how, I can't write that without writing a big mess on the blackboard. So you understand that this is the unit matrix where I take the k columns labeled by s, and then they're interspersed with this matrix a sub s. And these are the coordinates. These are the local coordinates in the patch u sub s. And then I think I'll leave the transition functions to the nodes. Now, as I also indicated at the end of last time, you can also put a Hermitian metric on Fn in the obvious way. So z norm squared would be the sum of zi, zi bar. That makes sense for quaternions as well as real and complex numbers. And then we can speak of orthonormal bases. And then v sub k of Fn, which is called the Steeple manifold, is equal to the space of k-dimensional subspaces with orthonormal bases. Okay, so by the kind of reasoning we saw before, this is equal to un, u appropriate to the field, ufn divided by ufn minus k. And then the Grassmannian, the same Grassmannian, can then be written as a quotient of the unitary group by uf k times ufn minus k. Okay, so as with our discussion of spheres and complex projective spaces, from this description, it's clear that over the complex numbers, I'll get a holomorphic manifold, a complex manifold. From this point of view, it's clear I'll get a compact manifold. And the other good thing about this point of view is that, you see, if I think of these, there are two good things that come out of this point of view. One is that if I think of these as k-dimensional subspaces, and now I'm allowed to give myself orthonormal bases, I can also say that this is the set of projection operators of rank k. Right? By projection operators, I mean an operator p from Fn to Fn such that p squared equals p. So you see it's 0 and 1 dimensional eigenspaces. Sorry, it's eigenspaces with eigenvalues 0 and 1 will be some subspaces. And if p has rank k, then it will have a k-dimensional subspace where p equals 1. Okay? And that's, to give such a, on the other hand, to give such a subspace, you can always define a projection operator onto that subspace with the other projection operator, 1 minus p, being onto the orthogonal subspace. Okay? Is it clear? Am I going too fast? Okay. So we can also think of this Grassmannian as the space of projection operators of rank k, and that will be a very useful point of view later on. And another thing that this makes clear is that, you see, when you have a subspace of rank k and you have a Hermitian matrix, then canonically there's an orthogonal subspace of dimension what? N minus k, right? So if I have a k-dimensional subspace, then there's a, canonically, if I have a Hermitian metric, canonically there's an orthogonal subspace of dimension n minus k. And so that explains very beautifully why there's this symmetry in these formulas between k and n minus k. So there's a nice duality between the Grassmannian of k-dimensional subspaces in n-dimensional space and n minus k-dimensional subspaces in n-dimensional space. Okay, so that just is a little quick overview of what I should have said last time about Grassmannians. Now, okay, so now I want to talk about a different subject, unless there are questions here. Okay, so what I'd like to talk about now is something about quotients by non-compact groups. But this is a big subject, and so we're only going to touch briefly on it. But I want to indicate some things. So we've seen that a principal G bundle can be thought of as a space P with a fixed point free right G action, so long as the quotient space P mod G is a nice space, a good manifold, and in particular Hausdorff. And so what I want to begin by showing you here is that when you're dividing by non-compact groups, some funny things can happen. Okay, so let me do that by example. So let's consider the 2 by 2 matrices over the complex numbers, M2 of C, and let's let the non-compact group, GL2C, act by conjugation. Now, this is not quite fixed point free, but that's not the main issue here. We'll see the main issue in a moment. So could we get a principal bundle over an orbifold, as it would turn out? Well, the answer is no, and let's see why not. So what are we doing here? We're taking the matrix, and we're taking it to its conjugate. And I guess I want a right action. And then we want to classify orbits under this action. Anybody want to volunteer what you think you would do to classify orbits? Well, what do we usually do with matrices when we conjugate them? Why do we conjugate matrices? To make them simpler. And what do we do? How do we make them simpler?
Put them into some canonical form.
Good. Right. So glad to see that it's a sophisticated class, and nobody said you want to diagonalize it. You can try and diagonalize it. So there's a subset of matrices that are diagonalizable, like that. And so you might say, well, it's just going to be, the orbits are just going to be labeled by pairs of eigenvalues Z1 and Z2. Well, first of all, that's not right. It's going to be unordered pairs, if anything. Z1 and Z2. And on the set of diagonalizable matrices, this quotient action is not so bad. It does have an orbifold singularity when Z1 equals Z2. But that's not what I'm after. That's not the problem. The problem is that there are also matrices which cannot be diagonalized, which have non-trivial Jordan canonical form. So for these matrices, we have a G inverse and a G, which makes it look like that, where lambda is not 0. Now, why are these matrices posing a problem in trying to make sense of the quotient space M2 mod GL2C, where the GL2C acts by conjugation. We're trying to make this into some topological space, and I claim that these matrices pose a problem. Okay? Now, why is that? Well, at this point, you might say we've fixed the gauge, right, when we put it into Jordan canonical form, but we haven't quite, because we can still conjugate by diagonal matrices. So we could conjugate by T1 inverse, T2 inverse, 1 lambda 0, 1, T1, T2, and then you work that out, and that's 1 lambda T1 inverse over T2 over T1, 0, 1. Okay? So that means that in this orbit, I can change around the lambda that I have in Jordan canonical form. So this and this is in the same orbit of the GL2C. Now, why is that a problem? Well, let's consider the equivalence class of this point, and let's of this matrix under conjugation, and let's consider the equivalence class of this one under conjugation, where lambda is not 0. So these are clearly two different points inside. These are 2 points, 2 distinct points in M2C mod GL2. Okay? They cannot be related by conjugation by any matrix, obviously, right? Because the conjugation of the identity matrix is the identity matrix, no matter what G is. So they're distinct points. But the question is, can they be separated in the topology? So what is an open set? An open set in the quotient, this is the definition of the quotient topology, and the quotient is one whose inverse image in M2C is open. Now, you see that this orbit here contains this matrix where Z is arbitrarily small. Because of this operation here. Okay? So this orbit, this point here, represents matrices with non-trivial Jordan form, but that lambda can be arbitrarily small. But any open set of the unit matrix in M2C contains 1Z01 for Z sufficiently small. Right? So imagine an open set. Imagine an open set in the set of 2 by 2 matrices that contains the unit matrix. How would you write such a set? Well, you would write 1 plus epsilon 1, 1, epsilon 1, 2, epsilon 2, 1, 1 plus epsilon 2, 2, right? Where the epsilons are small. So inside that open set, there are certainly going to be matrices like that. Just take 3 of the epsilons to be 0. But this matrix, you see, belongs to this orbit, which defines a different point. So these 2 distinct points cannot be separated. Okay? So that means that this quotient space is not Hausdorff. Okay, so let me drive that in by looking at another example, which is more closely related to the physical example I want to discuss. But it's a very similar phenomenon. So let's consider C2 with elements phi 1, phi 2. Sorry. Okay. Phi 1, phi 2. And let's consider the C star action where phi 1 goes to lambda phi 1 and phi 2 goes to lambda minus 1 phi 2. Now notice that if we were trying to make complex projective space, we would have put a lambda to the plus 1, but here I'm putting a minus 1 here. Okay, so now there's a gauge invariant combination, which is phi 1 times phi 2. Okay? Phi 1 times phi 2 is gauge invariant. Okay, so you might try and characterize the orbits by the value of this gauge invariant combination. Okay? And indeed, that's fine. So generic orbits will look like this. Okay? But then, if phi 1 times phi 2, if this gauge invariant quantity is equal to 0, there are 3 distinct orbits. And what are they? So there's O1, which is the set of phi 1, 0, such that phi 1 is not 0. O2, which is the set of 0, phi 2, such that phi 2 is not 0. And O3, which is 0, 0. Okay, so we have 3 distinct orbits. Now, supposing we try and make a quotient space. If we did what we do with complex projective space, and we took C2 minus the origin and divided by C star, we would have our problem with conjugation, the space of conjugacy orbits of 2 by 2 matrices. Okay, that's an exercise, but I hope it's clear. You see, the problem, again, would be that in this space, there are 2 points. There's the orbit O1, and there's the orbit O2. And these are really distinct points in this quotient space. Okay? On the other hand, by the C star action, I can make this phi 1 arbitrarily small. And I can similarly make this phi 2 arbitrarily small. So I can bring these guys as close as I like to 0, 0. Okay, so they cannot be separated. So these points, these distinct points, cannot be separated by open sets, which is the statement that the quotient space is not Hausdorff. And physicists generally gag at spaces which are not Hausdorff. You can hardly start writing actions or talk about local dynamics or whatever on a non-Hausdorff space. It is kind of an interesting space. I mean, it's a... Well, I'll tell you what the space is a little bit more in a second. Now, you might say, well, okay, let's just throw out all these orbits. Minus O1, union O2, union O3. Okay, these orbits are all troublesome. Let's just throw them all out and take that quotient. That space is okay, right? That is the space of orbits where the gauge invariant quantity, phi 1, phi 2, is not 0. This is a fine space, and in fact, this is just a copy of C star, and we can think of phi 1, phi 2 as being the thing that parameterizes the value in C star. Okay? That uniquely characterizes the orbit. Now, we can go back to this space then and see what's going on here. So this space looks like a copy of C star, but at the origin there are 2 points which cannot be separated. So it's C star, but then there are 2 points where there should be 1 at the origin, which cannot be separated from each other by the topology. So that's a kind of picture of that space, that non-Hausdorff space. But we can compactify this C star. We can compactify in 3 ways. You see, we could throw out 2 orbits. So we could throw out O1 union O2. We could throw out O1 union O3. Or we could throw out, again, 1 C star. Or we could throw out O2 union O3. In all of these ways, by throwing out 2 and just keeping 1, I've added exactly 1 point at the origin. So all of these spaces are C as complex manifolds. Okay? I've added the gauge invariant quantity phi1, phi2 equals 0, and I've only added in 1 point. Now there is a difference between these, as we'll see in a moment. Eraser. Okay. Now all of this is related to something called Kähler quotients and F and D terms in supersymmetry. So let me give you a very, very brief description of linear Kähler quotients. So let's consider the vector space C to the n. And this has a symplectic structure. So we can take coordinates, ZA, little a goes from 1 to n. We could write it in terms of its real and imaginary parts. And we could introduce the real 2 form, which is I over 2, the sum over a from 1 to n of dz upper a wedge dz bar lower a, which is, if you work it out, dxa wedge dya. So that defines Poisson brackets, if you like. Maybe you are happier with that. Xa, xb equals 0, xa, yb equals delta ab, and so on. And so we have here a phase space. Okay. And on the other hand, V carries a representation of UN, which preserves the symplectic structure. Now, when you have a group on a phase space that preserves the Poisson brackets, or preserves the symplectic structure, then the motions of that group are always generated by a Hamiltonian or a conserved charge. Okay? That's the general principle of Hamiltonian dynamics. So what is the conserved charge for the motions of UN? Well, a generator of a UN flow would be matrix T in the Lie algebra UN, which is n by n anti-Hermitian matrices. And the motion that it generates is delta ZA is T upper AB ZB, where T upper AB complex conjugate is minus T upper BA. Okay, so now let's write down the conserved charge. Well, to get the conserved charge, we first look at the vector field, which generates that motion. And that's, let's call it C of t, which is z upper b, t a b, d by dz lower a, minus z bar lower b, t upper b a, d by dz bar lower a. Okay. So you see C acting on z, or z bar, will generate just that motion, the action under unitary transformations. And the formula for the conserved charge is this formula. We take the contraction of our two form with this vector field, and then that is an exterior derivative of our conserved charge, which I'll write as mu of t. Okay? So you can work that out explicitly in this case, and mu of t, our conserved charge, our Hamiltonian, is z bar lower a, t upper a lower b, zb, up to a constant, which I'll call zeta of t. So, straightforward exercise to take this and check that it satisfies this criterion. So this is the conserved charge. Or the Hamiltonian. That generates these flows. Now you see, I can only determine it up to a constant because the definition involves the derivative. Okay, so in mathematics, in maths, mu is called the moment map. And moment map is short for momentum map because momentum is a famous conserved charge. And it's called a map because the mathematicians regard this as a function from our vector space, parameterized by the z's, into the dual space to the Lie algebra. So what that means is that if I give you an element of the Lie algebra, then I should get an honest-to-God function. And it should depend linearly on the element of the Lie algebra. So mu of t, so mu is the thing that takes, mu of zz bar, viewed this way, is the thing that takes t to what I called mu of t. That's pretty confusing, sorry. Let me call it mu of zz bar of t, and define this to be mu of zz bar. Okay, see this, for fixed z, this is in the dual of the Lie algebra. And therefore, this mu takes, given a z, I get an element of the dual of the Lie algebra. I see people puzzled. This is really kind of tautological, so is there any question about that? Are you with me up to the Hamiltonian here? Okay. So now we engage in some abstract nonsense that mathematicians love. Okay. So if I've got a z and a t, then I get a number. Okay. Okay. Now that number, you see, depends linearly on this t. It doesn't depend linearly on the z, but it depends linearly on the t. Okay, so mu of zz bar of t1 plus t2, a1 t1 plus a2 t2 is mu of zz bar is a1 mu of zz bar t1 plus a2 mu of z bar t2. Well, that's the definition of a linear map. Valued where? Well, these are numbers. Okay? So that means that mu of ZZ bar and then open slot is an element of the dual of the Lie algebra. Right? Because if I feed it in a T, I get a complex number. Is that clear? Yeah.
Is this sort of like a musical isomorphism in that sense?
A what?
Music. Oh, sorry. That's sort of weird. Like raising and lowering indices over going from the tangent space to the cotangent space for a manifold.
Well, it involves the dual of a vector space. In
Right.
that sense, it's similar to the relationship between tangent and cotangent, which involves the dual of a vector space. So I would say that that's the extent to which they're related. So given a z and a z, given a zz bar, I get an element of this dual space, and therefore mu is a map from the space of zz bars into the dual of the vector space. Okay, that's the moment map. Okay, so that's how the mathematicians think about this. It's actually a useful point of view. Right, now, I can define the symplectic quotient, at least the linear symplectic quotient. So supposing that I have some subgroup of UN, then I can restrict to the motions of that subgroup. Okay, I just take some SU2 subgroup or some U1 or something, some subgroup of UN, okay, acting on this big n-dimensional vector space. Then I can restrict to these motions, and then mu, when I restrict to those motions, gives me a map from V into G dual. So then the symplectic quotient of V / G is by definition mu inverse of 0 divided by G. Okay? So we take the solutions of this thing equals 0, and then that's G invariant, and then we divide that space by G. Exactly. Good, very good point. Now, up to now, I have said very little about these constants. In order for this to make sense, in order for this to be a G invariant set, this only makes sense if zeta of t is only non-zero for t in the center of my Lie algebra. Okay. So my zeta of t's, in order to do this, that constrains the constants I have. I can only have these zeta of t constants to be non-zero when they're in the center of the Lie algebra. So let me give you an example of this, which I hope will clarify it. So example 1, or it's the only example we'll discuss. So let's let V be Cn, and let's let G be U1. Okay? Just U1. That'll give us plenty of things to worry about. Okay, so now let's embed U1 inside UN so that the generator T of U1 looks like the diagonal of IQ1 through IQn, where the Q's are real numbers. Okay, so how does this U1 act on my coordinates? It's just this axiom, QA theta, zeta A equals 1, N. So I have that U1 action on my vector space. Well, you work out this, and you discover that mu is 1/2 the sum of QA ZA squared minus zeta. Well, you see, this is a commutative Lie algebra, so it is equal to its center. And in fact, I see that made a mistake in the notes. It should be minus, I missed the minus zeta there. Okay. So, what is the symplectic quotient? Let's see. How to. So what is the symplectic quotient? So if the QA are all equal to 1, then do you recognize the symplectic quotient? Something we've talked about? Pardon? Perfect. Right. So you see, well, and zeta is greater than 0, and zeta is greater than 0, then the symplectic quotient is equal to Cp n minus 1. And in fact, our vibration, this is equal to mu inverse of 0. Okay? If zeta is equal to 0, I just get a point. And if zeta is negative, it's empty. So you see that the space depends very much on zeta, in particular on its sign. It really matters. So zeta equals 0, we get a point. In fact, a point mod u1, rather singular. And if zeta is less than 0, the symplectic quotient is empty. But now you can play games with different choices of the Q's. For example, if the Q's are non-commensurate, then this action is actually an ergodic action, and it's not a U1 action, and it's rather an action of some universal cover of U1, if the Q's are non-commensurate. If the Q's are rationally related, then it's a good U1 action, but depending on what these, how these rational numbers are related, you can get orbifolds and other things. In particular, if the Q's are of opposite sign, you'll get a non-compact space. Okay, now all of this is related to F and D terms in D equals 4, n equals 1 supersymmetry. Supersymmetric field theory.
Excuse me.
Yeah.
So this construction always gives you smooth space. For generic C, always gets smooth space. Is that right?
No, you'll get orbifold singularities for sure. And you know, this kind of thing is a little singular. What you do get is a stack, but you can get a point mod U1, and you can get that kind of singularities at various points. So
Hausdorff.
yeah, I think yeah, good point. This is going to be Hausdorff because we are modding out by a compact group. So we're not going to have those kinds of problems that I was just indicating before with quotienting by non-compact groups. Okay, so in a four-dimensional supersymmetric field theory, where I'm not going to say exactly what that is, but let me just say that it involves the following data. So it involves a compact group, G, from which one gets the vector multiplet symmetry. It involves a linear representation, V, of dimension n, carrying a representation of G, possibly reducible. And we'll write coordinates for that, phi upper A equals 1 through n. So these phi should be thought of as analogous to these z's. And then you need three functions. You need a real analytic Taylor potential from V to R. You need something called a gauge kinetic term, which we won't need. And you need a superpotential, which is a holomorphic function from V to C. And the final piece of data you need are what are called phi A Iliopolis terms, which is a map, zeta, from the center of the Lie algebra to R. So that's the data you need. And now if I take the simplest version of the gauge kinetic term and the Taylor potential, I didn't mean to erase that. Okay, come back to it. If I take the simplest version of the first two functions, then the potential energy for constant scalars, constant in space-time, scalars, and zero gauge fields is just U equals dA dA plus the gradient of dW squared, where dA is equal to the moment map evaluated on generators of G. So TA is a basis of generators of our Lie algebra G. That's why I was telling you about the moment map. Okay? So these expressions here are how you get your kinetic energy, your potential energy. Okay, so then if you want to look, so this is a very important formula. It's a sum of positive terms. So the manifold of classical vacua, let's call it M classical vacua, is the set of phi such that dW equals 0, intersect the set of phi such that mu equals 0. And I guess I should have said that the superpotential clearly has to be gauge invariant. So W is G invariant holomorphic function. And we've seen that since the phi Iliopolis terms are in the center of the Lie algebra, mu of 0 is equal to 0. So I can take this space, I can mod out by gauge equivalence. So that's the space of classical vacua. And that's a very, very important thing to understand in understanding supersymmetry. This is the set of possible vacua, then there are non-renormalization theorems and so on that says that this is, at least in some conditions, in some circumstances, this is the set of quantum vacua, and you want to know, what is it like? Because the physics changes as you move around on this vacuum. Yeah.
So in this sense, can we think of zeta as an order parameter of some phase transition?
Yes, absolutely. So changing phi Iliopolis parameters, as I've started to indicate here, can make very dramatic effects on the moduli space of vacua. That is correct. Okay. Now, here comes some important physical intuition. We should be able to describe the space of vacua by the chiral gauge invariant operators. And indeed, since W is gauge invariant and holomorphic, W is G invariant and holomorphic, that implies that W is actually GC invariant, where GC is the complexification of the gauge group. So if this were SUN, then GC would be SUNC, SLNC. If this were UN, the complexification would be GLNC. If this were U1, the complexification would be G star, and so on.
Sorry, can you explain why this arrow? Why this arrow is?
Why? Which arrow here?
The W is G invariant.
Okay, W is G invariant and it's holomorphic. So what am I doing? I'm simply holomorphically extending delta phi. So we have delta phi A. Let's see, delta phi A T A B dW by d phi B equals 0. Now, what am I going to do when I extend my compact gauge group to my non-compact gauge group? Well, I'll multiply these generators by I. Okay? So it's still true for the generator with I times TA. Okay? So this is the change of phi under the complexified gauge transformations. And so it's clearly still true.
But why do you need W to be holomorphic? I mean, that's kind of.
Why do I need W to be holomorphic? Because I have not given the. I'm not giving a course on supersymmetry.
I was asking why the holomorphic is important in this arrow. If you don't have this, you wouldn't get W to be.
Oh, well, if W, well, for example, the Kähler potential is not GC invariant. So if I simply had.
No, but these arguments are simple. I just multiply by I in front of it.
No. Because then I'll get relative signs, because I'll have derivatives with respect to phi and phi bar, you see. So, okay, this is an important point. So, you see, the Kähler potential, being a physical thing, must also be gauge invariant, and therefore we should also have that condition. That expresses the invariance of the Kähler potential, which is just real analytic. That expresses its invariance under the compact gauge symmetry. Now, what would these are the changes of phi under this compact gauge symmetry. If I complexified my gauge transformation, I would have an I here and a minus I here. So that doesn't follow anymore. You see, that doesn't trivially follow because there's a relative sign here. Whereas with W, if we have that equals 0, it automatically follows that multiplying by I is 0, but that is the change of phi under the complexified gauge transformation. Is there any question about that? Is that clear? Okay. So our superpotential is G invariant and holomorphic, and therefore invariant under complexified gauge transformations. And therefore, if you accept this physical intuition, you should also be able to define the space of classical vacua as the set of phi such that dW equals 0 divided by the complexified gauge group. But we've just seen that division by the complexified gauge group is a treacherous thing. Okay? So there's a mathematical theory which tells you how to divide out by these non-compact gauge groups. It's called geometric invariant theory. And it is a systematic way to throw away certain bad orbits so that the quotient space is a good space, a nice Hausdorff space. Now, we saw a very simple example of that geometric invariant theory when we looked at, this is what I didn't want to erase, when we looked at our pair of, now we think of them as chiral multiplets, phi1 and phi2, and we have the gauge group action, the complexified gauge group action, like that. And so then remember that we could take C2 minus O1 union O2 and divide by C star. We could take C2 minus O1 union O3 divided by C star, and we could take C2 minus O2 union O3 and divide by C star, where O1, I remind you, was the set of phi1 not equal to 0, phi2 equals 0, O2 was phi1 equals 0, phi2 not 0, and O3 was phi1 equals phi2 equals 0. Now, there's a beautiful correspondence between that and taking this scalar, the symplectic quotient. So let's compare that with the D term we get. So the D term would be phi1 squared minus, because it has charge minus 1, minus phi2 squared minus zeta. So we want to solve D equals 0. And I'm taking the superpotential W equals 0 in this example for simplicity. So we want to solve D equals 0 to get our vacuum manifold. Well, let's ask what GC, which is C star in this case, orbits do we associate with solutions? Okay, well, suppose first that phi1, phi2 is not 0. Okay. If phi1 is phi2 is not 0, then let's look at the value of the D term, the value of D on the orbit is going to be lambda squared phi1 squared minus lambda to the minus 2 phi2 squared minus zeta equals 0. Well, okay, you see, by making lambda very large, I can make this thing large and positive. And by making lambda very small, I can make this thing large and negative. So there's no problem. I can always solve this. Okay? But the problem, we're not surprised to see, will happen on the orbit where phi1, phi2 equals 0. If zeta is equal to 0, we can solve D equals 0 on O3. Clearly, because O3 is phi1 equals phi2 equals 0. But not on O1 union O2. Right? Because on O1 union O2, or O2, one of the phi's is not equal to 0, but the other one is 0. So this is either always, remember, zeta is 0 here. Then this is always positive or always negative. Can't solve it. So on these orbits, D does not take on its minimal value. Or better to say, D squared, because D squared is the physical potential energy. So you'd see D squared there on O1 union O2, the physical potential energy does not take on its minimal value. Okay? If zeta is greater than 0, okay, we can solve D equals 0 on, which one is it? O1. But not on O2 union O3. Same story. If zeta is positive, if phi 1 is not 0, and phi 2 is equal to 0, okay, I can solve this. Right? Right? Is it clear? Will we wait? So then I can solve this, but I cannot solve this on the other orbits. And again, D squared does not attain its minimum on O2 union O3. And finally, of course, if zeta is less than 0, we can solve D equals 0 on O2, but not on O1 union O3. Well, now you see this beautiful correspondence with our three ways of compactifying the holomorphic quotient. And so that is, in essence, the main theorem in the relationship of geometric invariant theory to the symplectic quotient, which is there are these different ways of taking the symplectic quotient corresponding to these different signs of the phi A Iliopolis terms. Okay, and they correspond to different ways of throwing out the bad orbits and keeping some good orbits so that you have a nice compact variety. This is very deep and difficult subject, and so we're not going to go into any more detail about it right now. But I give some references if you're interested in this. It's very relevant if you're thinking about vacua of n equals 1 supersymmetric theories. Okay, it's getting late, but we're also getting far behind, so I'm going to do the next section. Are there any questions about this? Okay, so now we're gonna make a real change of gear. We're going to get back to our main theme of this chapter on principal bundles and start talking a little bit about classification of bundles. And the first and most fundamental question we could ask about classifying bundles is, what can we say about classifying principal G bundles over a sphere? So I'm going to answer that question, and then we'll quit. So, classification of principal G bundles over a sphere Sn. Okay, now based on what we saw of the Hopf vibration before, it should be pretty clear how we should approach this subject. So we should take our sphere and we should look at the equator, which is Sn minus 1. And we should take our north and south poles. And we should define, let's call it, a cell, Dn plus, which is homeomorphic to Rn. find the cell dn minus, including the south pole, but not the north pole, which is also homeomorphic to Rn. So that means that our bundle, wherever it is, becomes trivializable on d plus and d minus, because that's a contractible space. Okay? So therefore, we only need one transition function. Let's call it g plus minus from Sn minus 1 times an open interval to g. And you see, this contracts to Sn minus 1. So all the topology is simply captured by our transition, or our clutching function, as it's sometimes called, g plus minus into g. Okay, so now recall that we can always change the gauge. So we can always change the gauge by functions L plus from d plus to g, and L minus, continuous functions, from d minus to g. And that gives us a new transition function, which gives us an equivalent, an isomorphic principal bundle, which has those transition functions. Remember that? Remember I told you that if we can make a bundle by gluing together on overlaps with these g alpha betas, and then I explained that I could change the trivialization by locally defined functions. I call them L alpha. Maybe if I use a slightly different notation, it will jog your memory. L alpha inverse, G alpha beta, L beta. Remember that discussion? So I'm applying that here. Okay? And so all I want to do right now is try and say what's the invariant under this change of gauge of such a bundle that I've made with this clutching function. Okay, well, let's warm up with the case n equals 1. So we have G bundles over a sphere. And in this case, and only in this case, our overlap region is disconnected. So we have u plus minus right and u plus minus left. And the essence of the matter can be obtained by taking G to be discrete. And in the notes, I generalize it to G, which is not discrete, but let's just take G to be discrete. Okay. So now, I have a G plus minus right over here and a G plus minus left over here. Okay, now clearly, by choosing lambda plus and lambda minus judiciously, I can set G plus minus right to be 1. You know, if you start with a G plus minus, I simply choose the lambda plus, say, which is the inverse, and then over here it's 1. But that doesn't completely fix our gauge freedom. So G plus minus right equals 1 leaves gauge freedom. And the gauge freedom is lambda plus equals lambda minus. You see, if I make a further choice of gauge, I want to keep G plus minus right equals 1. Okay? That fixes lambda plus here to be lambda minus on this overlap. Now, because I have a discrete group, it has to be constant throughout the rest of the patch. It's a continuous function. Okay? So lambda plus was defined up here. Lambda minus was defined over here. On the overlap region, I have to have lambda plus equals lambda minus to keep this gauge. And therefore, lambda plus equals lambda minus over here. So that means that g plus minus left is conjugated to lambda plus inverse g plus minus left lambda minus, which is the same. So I'll just call it lambda inverse g plus minus lambda. Okay. Now, pi naught of a topological space in general is not a group, but pi naught of a Lie group is a group. And if G is disconnected, it's canonically the same as G. If G is just a discrete group like a Zn, it's just G itself. So what we see is that isomorphism classes of principal G bundles over S1 are in one-to-one correspondence with conjugacy classes of pi naught of G. All right, so I think since in view of the time, rather than go on to higher spheres, I'll just give you an example, okay, for the discrete group. And then we'll, next time, which remember is next Monday. I'm not going to be here on Wednesday. Okay? Next time on Monday, we will take up the case of higher n. But let me just finish with an example here. So I remind you that when my first example of a principal G bundle was to take the unit sphere in complex number space, complex numbers of phase 1, and we took a pi, which took z goes to w equals z to the n. You remember that, right? And the fibers are a Zn torsion. Namely, the fibers have a transitive fixed point free action of Zn. What are the fibers? The fibers are the different nth roots of W. So this is a non-trivial bundle, as I explained. If you try and make a global cross-section of this principal G bundle, a global cross-section would be taking an nth root. Z equals W of 1 over n. But you know you can't do that without choosing a cut. You know there has to be a discontinuity. Okay? Since you don't have a global nth root around the origin, you can't trivialize this bundle. Okay, but now we see that for any element of Zn, you see Zn is abelian, so the set of conjugacy classes of Zn is the same as Zn. Okay. So for any element of Zn, I should be able to make an inequivalent principal Zn bundle. Okay. And we see from this construction more or less how we should do it. As we go around, we trivialize it on the interval, and then we glue this end to this end by multiplying by omega to the j, let's say, or omega to the m, where omega is e to the 2 pi I over n, and m only is an integer modulo n. Now, actually, there's a very beautiful description of these bundles, which is analogous to this description here. is something I was wondering about, and Pan asked me, and I didn't know the answer, but now I figured out the answer, so let me tell you. So, consider the set of Z and W such that Z to the N equals W to the M as a subset of U1 times U1. Okay? So U1 times U1 is the torus. Okay? So we're looking at something like a copy of U1, which is sort of wrapping around in general. All right? Okay. Well, there's a projection here to W. Okay, let me say that better. So this will be our principal bundle P and M, and there's a projection from P and M down to S1, which takes Z and W, satisfying this equation, down to W. Yes, sir?
Is this like saying that we could take an n-twisted Möbius strip by wrapping a sheet around the torus?
It's a lot like twisting up the Möbius strip, but if you twist the Möbius strip twice, it is, as a principal Z2 bundle, trivial. Of course, it gets twisted up in space, but that has to do with its embedding in space.
Yeah.
Okay. As an intrinsic bundle, it's two torsion. But it's similar. It's certainly similar that I'm squaring the transition function, or taking the nth power of the transition function. Okay, so there is this projection from ZW to W. Okay, and that's a surjective projection. And now you can ask, what is the fiber? Well, if I'm given W, I can compute W to the M, and then what are the elements of the fiber? Those are the different roots of Z. So the fiber is again a Zn torsive. So this really is a principal Zn bundle. And moreover, what are the transition functions? Well, let's try and find a global cross section. What would a global cross section be? It would be W goes to Z, and Z, you see, is W to the M over N. And now as I go around the origin in the complex W plane, of course I'm going to have to find a cut. And what's my discontinuity? My discontinuity is by omega to the M. So that's exactly the transition function I want. So this is a description of these bundles. Okay, so next time I will complete the discussion of how you classify principal G bundles over spheres, and then I'll indicate something of how that theory generalizes to something called the universal bundle and the classifying space. Much more abstract, unfortunately. That's fine.